Hello. Welcome back, everybody. Okay. Okay. Hello, welcome, everybody. How are you all doing? Happy start of your week. Happy Tuesday. Um. Okay. So, welcome back. We're still doing this today. I'm streaming a little bit earlier. Today I decided to just switch it to like in the middle afternoon. I feel like people have finished, like for those in university, like they just finished exams, so you're gonna have some more time to watch. And also I think this time is just more convenient for me, or I want to try new stuff, so I wanted to start today at a little bit earlier. But let me know, like just in the chat or whatever. Let me know if like you would rather a different time. I could probably like make like a poll or something. But honestly, I'm just gonna try and still do what works best for me. Um, yeah, how was everybody's weekend? My weekend was good. So like on what was it? Saturday? Yeah. On Saturday there was a convention here for like a convention, like a geeky convention type thing. It's called CarlitoCon. And so I went there on Saturday. It ran from like 9 a.m. to like late, probably like 6 p.m. or whatever. And so I went to that. I checked out the vendors. Some of my friends were actually like selling cards, like Pokemon and Lorcana cards over there. So I went to check them out. Sat down, played some board games for a little bit, and then I had my. Oh, actually, before that, I got this from a vendor at CarlitoCon. I thought it was nice, and so I'm just gonna add it to a list of my all my garbage that I have here on my desk. Like I have this. I also opened some packs at CarlitoCon. Got this Aurelia from Riftbound. I have like a little Columbia keychain. I have a little skull. I have a bunch of like weird stuff here on my desk, just like fidget toys and stuff. So yeah, on Saturday I went to that convention. Checked it out for like a couple one hour and a half or something, and then I had to head over to my local game store because there were set champs. For those of you who don't know what set champs are, they're it's like a competition for Lorcana. So every set, which is like a release of a different set of cards and different like packs you can open that have different cards. It's a new set for the game, and at the end of the set or towards the end, they do set champs, which is like a store championship, where now that you've been able to experiment with the cards and build your decks, you can like compete to see who's the best. And because it was happening at the same day, at the same time as CarlitoCon, we didn't have a big turnup, but that kind of played in my favor. There was four of us, and we played. Hello? Can you hear me now? You should be able to hear me now. I switched the mics. I don't know why that wasn't working. Give me a second. Oh, I I see. My Nvidia broadcast just decided to like not work today. Let me change it back. Let me know if you can hear me after the switch. Hello? 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 Okay, you should be able to hear me now. Okay, I was saying basically this weekend I went to my local, so there was a convention here where I live for like geeky stuff like Pokemon cards, cosplay, D&D and all that sort of stuff. And so I went to that to check out the vendors. Some of my friends were like selling Lorcana cards, and they're also selling like Pokemon cards, so I checked them out. I played some board games there. They weren't actually doing any tournaments for the games I play, so I didn't play there, but they were doing tournaments for Warhammer, for the Star Wars Unlimited game, for I think Magic the Gathering or something like that. But I checked them out, opened a couple packs. I got this from a vendor just to put on my list of garbage that is here down on my desk. I opened some Riftbound packs and got this Irelia. I thought was really nice. It's the same like the splash art from the League game. And then that same day we had Set Champs, which is basically like a competition for Lorcana for like our store. So whenever a set is released, you're given time to like experiment with the new cards that come out, open some packs, build your deck, and at the end of the set or like the season, let's say, they do like a store championship where you compete with the decks that you've been experimenting on. And try to figure out who's best. So normally for that they give prizes to the top 8 players, but because we had everybody at CarlitoCon pretty much, that was the convention that was happening that day, we had only like 4 people show up to set championships, so everybody got pricing, and we only did like 2 matches technically, like the first one, and then if you won you played for finals, if you lost you played for 3rd and 4th place. I won my first match and then lost my second one, so I technically got 2nd place, but it was my first at champs, and I'm happy with the result we got. I got like, okay, I can actually show it, give me a second. I got this Tinkerbell. Actually, let me flip my camera so you can actually read it. Horizontal. Okay, so I got this Tinkerbell, which actually I thought it was like, this is the pricing for top 8, so it's actually pretty rare in like other stores. And this card actually, normally these same cards for like previous seasons are like $20 at most. This one's 40 American, so I was pretty happy. And they give out like one of these to like every contestant, but it's not shiny. And then to top 8 they give you like a shiny one, so if I pull it out you might be able to see like the glow. Not really, but it's like a little bit shiny, and like that makes it worth like, I don't know, like $40 more than the other one. So I got that from my set champs. And yeah, and also like the lady there just like decided to give out like a whole box of packs to in between like the 4 of us, so I got to like open like a shit ton of packs as well. So I was pretty happy about that. But anyway, it's been like 10 minutes, so I think I can start getting into what I wanted to do today, and that is we're gonna do some lead code, continuing what we were doing last time. So we're just gonna run through like the Grind 75 list just from top to bottom. But before that, let's do the Lorcana card of the day. So as you know, every stream I pull a random Lorcana card using this program I made. And that's going to be the Lorcana card of the day. I'm just going to talk a little bit more about that. So let's run the script. And our Lorcana card of the day is a Fang Crossbow. It's a 3 cost. It's Sapphire, which is like the color of the card. It's blue. 3 cost item. Items are cards that you play, and then they stay on the field, and then you can use them in some way to like help your game state. And it says you can exert it, that's what the symbol means, and pay 2 cost, and so like pay 2 ink. And ink, so you can convert the cards that have this like little like yellow thing around them, you can convert them into resources, and then you can use those resources to play other cards. So this one, for example, you need to pay 3 resources to play it, and then to use this effect you need to exert it, which means turn it sideways, and then pay 2 cost.
And it says chosen character gets -2 strength this turn, so -2 attack. You give -2 attack to any character. And then you can also exert the card, banish the item, and then you can banish a chosen dragon character. And this card is actually not. I mean, I think it depends on the meta, but it's not. I don't. First of all, it's not on the current set of like legal cards you can play, because they've rotated out all these older cards. This is a card from set 2. We're on set 11 right now, so they've rotated all of the older cards from sets 4 and before, and they've reprinted some of them, but this one wasn't reprinted as far as I know, and it's not amazing. I mean, dragon characters are not that common. I think there's the Maleficent dragon that you play in Ruby. I can actually show that. There's the Maleficent dragon that you play in Ruby, but there's not a lot of like dragon characters. I mean, let's see. Characteristic dragon. There's the Sisu, but people are not playing a lot of Sisus right now. This genie is sort of popular. Am I sorting by popularity? Let's sort by popularity. Yeah, so Maleficent dragon, the Sisu. This Mushu, I haven't seen it in so long, but honestly, people don't play Ruby in my local game stores. Honestly, it's not that common, and it would depend on the metagame, but also, I feel like paying 3 to banish a dragon character, you have other ways of removal that are better. Like, you have, for example, this one that they reprinted called Let It Go, where you can, well, this one costs 5, but you can put a chosen character into their player's Inkwell face down and exerted. Or you have one that is blurple, so like blue and purple, it's an action. Let's see if it's anywhere close to here. Oh, Into the Unknown. This one costs 3 and does the exact same thing. You put a chosen exerted character into your player's Inkwell, face down and exerted. So that item is like, this cost to like get -2, it can be nice, but I feel like it's a little bit steep. Maybe not for Sapphire, but still, like, it's a little bit steep and situational. Like, in some metas, you're not challenging all the time. So yeah, this item not great, but it's the Lorcana card of the day. Other things here, it's this is the artist, Antonia Fleshig. It's card 166 out of 204 in English, set 2. It's an uncommon, and it's from Disney. So yeah, that's the Lorcana card of the day. And this is Grand 75, so we can move into our normal programming. Let me start setting up my environment beforehand. Speed code. Okay. Just close that for now. And then let me open Paint. Might as well. Okay. So binary search. Okay, I'm excited about this one because the explanation is nice. It says 704 binary search. Given an array of integers, okay, so 704 binary search. Given an array of integers, nums, which is sorted in ascending order, and an integer target, write a function to search target in nums. If target exists, then return its index. Otherwise, return -1. You must write an algorithm with O log n runtime complexity. In example 1 here, we have this list of numbers, and we're trying to check if 9 exists, and if so, we return its index. So you can see, obviously 9 is right here, it's index 4, if you count 0, 1, 2, 3, 4. So you return 4. And then this one is target 2. 2 is not in the list, so you return -1. So pretty straightforward. Let's check some of the constraints. In the constraints, it says that the length of the numbers is 10 to the 4 at most. And the numbers themselves and the target are anywhere from -10 to the 4 to 10 to the 4. So this should fit in an integer, I believe. And all the integers in nums are unique. And nums is sorted in ascending order. Okay, so couple things. So, okay, first of all, then the title of the problem actually gives you a hint into exactly what algorithm you should use. Also, you're given another hint here. It says you must write an algorithm in O of log n runtime complexity. When we're talking about log n in programming, we mean log 2, base 2, log base 2. Not log natural, not log 10. We're log base 2 because we're normally dealing in binary. And another hint you're given is that nums is sorted in ascending order. So this is important because you need to. It's not random, right? Because they could give you a list in any order, but they're telling you explicitly it's in ascending order. So this must somehow come into the answer of the problem. And this we're gonna solve with an algorithm called binary search. And so binary search is a pretty known algorithm. This is a pretty common problem, in fact. Like, you have a list of things and you're trying to look up if there's a thing in that list, a specific thing in that list, and you have to deal with that problem constantly. So a lot of very important software is built on top of this algorithm. So let's go into Paint, and actually I'm gonna steal a little bit from the CS50 explanation. CS50 is a course about computer science fundamentals. If you're looking to pivot from like a different career that's not software into like software and programming and all that stuff, or if you're just into programming but don't know where to start, I would recommend taking that course. It introduces you to all the fundamentals of computer science and how to program, and it takes you from zero to actually building some pretty interesting projects. But they do this very interesting explanation in CS50, and they do it with a phone book. And just so I'm a little bit different, I'm going to do it with a dictionary, okay? So let's rephrase the problem. In this problem, you're told you have a list of numbers. You're trying to check if a specific number exists in that list. In my problem, I'm going to change it to you have a dictionary of words. Let's say this is the Oxford Dictionary. The Oxford Dict. And you're trying to look where a specific word, which page a specific word is in, right? So let's say we're trying to look up where the word dismantle is in this dictionary, which page it is in. So how would you do it as a normal person? You were trying to, like, the way I would do it, for example, is I know that the dictionary is sorted alphabetically, so we're trying to more or less calculate where the D would be, and then trying to open it to that page. And then if I'm below, like I say, if I'm like letter B, I need to go to the right. And if I'm above the D, if I'm like letter X, letter M, then I need to go back because it's before, because it's sorted in alphabetically. Natural reads. Yep. And so a computer, like that first step I told you, where you like estimate where it would be in the dictionary, a computer can't really like estimate. And also, like, our estimates, we do it based on experience, but they might not be accurate. You could say, oh, I think it's in this page because there's a lot of letters that start with A and a lot of letters that start with B, but you don't know exactly how many letters, and your estimation might be completely wrong. This dictionary might have a lot of letters after and not a lot of them before, so your page might fall earlier or later depending on your use case. But we can take some insights from the process I just told you, whereas like if you see that the page you opened it at is later than the letter you're trying to look, then you're gonna look like in the part earlier. And then another thing we can use to discover this algorithm is log to, like, we're told that the complexity, so how many steps it's going to take us to solve the algorithm, in the worst case, is going to be log 2 of n. And log 2 of n is characterized because it's, you can get log 2 of n if you have n things. Log 2 of n would be the same as, like, having, like, separate, like, taking out half of your amount of things every time, right? So if you have a list of like 6 things, you divide it in 2, now you have 3, you divide it in 2, now you have 1.5, you divide it in 2, now you have 0.75, and that is log n, basically. That is described by log n. With all of this like previous explanation, now let's go into the actual algorithm. So how a computer can actually solve this. So let's continue with this example. You have the Oxford Dictionary, you're trying to look for dismantle. So what you're gonna do, so you can discard the most amount of things, and you're using that insight of like having your total number of things, is that you're gonna open the dictionary to the middle. right? So you're gonna try to find the middle of the dictionary and open it there. So let's say my dictionary has 500 pages. We're gonna open it at page 250. Why? Because that allows us to discard half of the dictionary. So we open at page 250, and then we check, is my current page, does it start with a letter that goes after or before my word? So let's say in my current page, the first word is probably something like mince, starts with M. So we know we need to go before. So we're gonna get rid of all of the later half of that dictionary. So because we open at mince, we know that all of the pages after mince are gonna be letters after M. So we can discard all of that right half of the dictionary. And now we can look in these first 250 pages. Now we reduce the problem to 250 pages. Now we're gonna open to the middle of these 250 pages. So we're gonna go to page 125. And let's say at page 125, the word is something like fluster. I'm using like very fancy words for whatever reason, but let's say the word is fluster. So then you're gonna check, okay, it starts with F, and F goes after D. So everything after F is gonna be bigger than the word dismantle, right? So we can get rid of pages 125 to pages 250. We don't need to check those because we know it's not going to be there. So we get rid of this half. Now we check in the middle of this, and that's going to be page 62.5. That would be the middle of like 125. Since there's no like half pages, we're just going to round down. So we're going to round down to 62. And we round down to 62, and let's say the word is something like cluster. So we know cluster goes before dismantle, right? Because it starts with C and D goes after C. So we can get rid of pages 0 to 62. We don't need to check those pages anymore, because everything that goes before cluster, dismantle is not going to be in it. Okay, so we can get rid of pages 0 to 62, and now we're only focused on pages 62 to 125. Now we go and check the middle, like the middle of those, and the middle of those you can calculate it with this formula. So it's going to be 62 plus 125 over 2, and that's going to give you the half in between those two. And I'm going to just use the calculator for this. 62 plus 125 over 2. That's going to be 93.5. We're going to round down. We're going to round down to 93. We're going to open at page 93. And then we're going to keep doing this process. And eventually, we're going to reach our word. Because we're going to keep having, like, we're going to get half of the pages. And eventually, you're going to reach a point where you have, like, 2 pages. Then you take half of that and you only have 1 page. And if it's not in that page, you know it's not in the dictionary at all. Because you've checked all of the possibilities in a smart way using binary search. Now the actual algorithm, now that I've explained like how it works, let's write a little like pseudocode for the algorithm. So you're gonna have a left and a right pointer, which is gonna be your minimum page and your maximum page that's in the range that you need to check still. So at the beginning, L is gonna start as 0, and R is gonna start at the end of your dictionary. In our case, it was 500, where we're gonna call it M. Then we're gonna get the middle of these two, and that's gonna be, the formula is gonna be L plus R over 2, right? After you get L plus R over 2, you check that page, or that index in our case, in like the case of the problem, you check that index, and then you compare it with your target. If that index is less than your target, then you can discard. So this is going to be, we're going to call it M. M is going to be for the middle. So if the item at M is less than your target, you're going to discard the bottom half, the left half. Actually, let me flip my camera again. Okay. If your target, if whatever element it's in the middle is less than your target, you can discard the left half of your total list, because you know the target's not going to be in that side. If it's bigger than your target, you discard the right half. If it's equal to your target, great, you found the answer. It's at the middle. Like you return this index because this is the page or index where your target is. And you're gonna keep doing that. You're gonna keep having your total list until you get your result. Okay? And so let's program it up. So I'm gonna, is this big enough? I'm gonna make it maybe a little bit bigger. Yeah. So let's do envim array, and then it's problem 704.cpp. And then let's go here, copy this, paste. Perfect. So, like we said, we're gonna have a left and a right, like, pointer, like in our case. And so L is gonna be equal to 0. We're gonna start it at the beginning. And R is gonna be equal to nums.length minus 1. Right? Because we zero index, we don't include the last part. Actually, it's nums.length minus 1. We have L and R. Then we keep checking while L is less than R. Because if L is equal to R, we only have one page left to check, and we can do one final check. If L is bigger than R, because like I said, we're like flooring the answer, and like that sometimes makes R be like less than L, that means we've checked all of the indexes we need to check, and we don't need to check anymore. So this is going to be our end condition. While L is less than R, we're going to calculate M. So M is going to be equal to L plus R over 2. And that's going to be rounded down because of integer arithmetic, so you're going to remove the decimal if it's like an odd number and you're dividing it in half. Then we check the item in the middle in index M and compare it to the target. And then based on that, we recalculate our left and right pointers. So if target is less than nums mid, so like the number in the middle. So if it's less than it, we discard the right half. So R is gonna become n minus 1. Like our new right pointer is gonna become the page before the middle, because we already know that it's not in the middle page, so we can discard even the middle page and everything after. Else, if target is bigger than numsem, then L is gonna be m plus 1. We're gonna, if our target is bigger than whatever's in the middle, we're gonna only check the right half, so we discard the left half. The left half including the middle, because we already checked that it's not in this page. And if it's not smaller and it's not bigger, that means we must have found our target element, so we can return M. At the end, since we like finish checking once L and R are the same, or once L and R are like the same or like overlapping, we need to do a final check to see if like the final page we need to check if the element is there, right? And so you have to be very careful in how you program this, and I'm gonna just try this out, but I think you can probably check. We can return here if nums L is equal to target, return L, otherwise return -1. Okay? And this is gonna be our whole algorithm. So like I mentioned, running it back, you have a left and right pointer that you start at the beginning, at the end of your list. While those pointers don't overlap, while you still have like a section of the list to check, you get the middle of that list, you check the element at the middle, you compare it to the target. If the middle is bigger than the target, you discard the right half and you only check the left half. If the middle is smaller than the target, you only check the right half and you discard the left half. And if the middle is the target, then you return the index of the middle. And then at the end, you do this final check because you might have skipped a check because of the way we're doing it. Like, I think you can do this in multiple ways. You could probably do less than or equal to, and then you might not have to do the final check or something, but I think this just works best because if you do less than or equal to, if you do less than or equal to, then it becomes stuck in like a final, like an infinite loop. So this is better because if L and R become the same, then let's say L and R are 5 and 5, then when you do this calculation, then it becomes 5 plus 5 over 2 is 5, and then one of these might happen, in which case you skip it. But if it's your target, actually you might be able to less than or equal to R, now that I think about it. Yeah, okay, maybe let's do that. Maybe it's easier to understand that way. So if we ever exit that loop, means we didn't find it. Otherwise, we just check everything. Let's try it out. I might get like an infinite loop, but that's we're learning. I mean, I should know this already, so shame on me. No member name length. Oh, it's size. Right. I always mess these up. Okay. Size. Length is for strings. Okay, awesome. We found our elements. And we submit. Perfect. Look at that. Beats 100%. Let's go. Okay, binary search, done. Okay, flood fill. You're given an image represented... Okay, 733 flood fill. You're given an image represented by an m times n grid of integers image, where image ij represents the pixel value of the image. You're also given 3 integers, SR, SC, and color. Your task is to perform a flood fill on the image starting from pixel SRSC. To perform a flood fill, begin with the starting pixel and change its color to color. Perform the same process for each pixel that is directly adjacent, that share a side with the original pixel either horizontally or vertically, and shares the same color as the starting pixel. Keep repeating this process by checking neighboring pixels of the updated pixels and modifying their color if it matches the original color of the starting pixel. The process stops when there are no more adjacent pixels of the original color to update. Return the modified image after performing the flood fill. I'm not sure I got that on the first read, but I think the example would make it clearer. So you're given this grid right here. You're given your SRSC, so the place where you start is 1 and the color is 2. And then what you do is you begin to start at the starting pixel and change its color to color, so you change it to 2. Perform the same process for each pixel that is directly adjacent. So adjacent, I assume, is just like because you can have 2 types of adjacency. You could have it like it's just this one for this one. It's just this one, this one, this one, this one. Or you could have it being all around. I think in this case they say either they share a side with the original pixel, either horizontally or vertically. So this doesn't share a side with it. So it would just be top, bottom, left, right. Keep repeating, perform the same process for each pixel that is directly adjacent and shares the same color as the starting pixel. So if this starts at 1, we change all of the ones that were 1. Keep repeating this process by checking neighboring pixels of the updated pixels and modifying their color if it matches the original color of the starting pixel. The process stops when there are no more adjacent pixels of the original color to update. Return the modified image after performing the flood fill. So I can think of two ways we can do this. Let's see the constraints first. So M is going to be equal to image length, image I div length, N is going to be equal to image I length. That doesn't really help it. I mean, I guess it just tells you like the vertical, which one's the vertical, and which one's the rows and which one's the columns. M and N are going to be less than 50. Image IJ, so whatever number is here is going to be less than 2 to the 16, so it's going to fit in a 32-bit integer, and also the color will fit in there, and the SRC are less than or M and N. So I can think of two ways of doing this, because we just have to follow the algorithm, but the implementation is like the part that might trick you up. So there's two ways I can see this. We can do a recursive way, and we can do an iterative way. I'm gonna go for the iterative way because I like iterative solutions. Recursive, I think sometimes like, oh, it's like really easy to program, but then it kind of like escapes how it ends up working like in your head, and it's easier to understand if you do in an iterative way. So I prefer to do iterative solutions. So what we're gonna do is we have our grid. Correct? And then we have our grid, and then we have our starting position. So I'm just gonna copy this one, 1 1 1 1 0 0 1. Okay. So we're gonna start here, and we're gonna record the starting color. So the starting color, or in this case they call it, yeah, let's call it color. Let's record it as 1, and we don't ever need to change this because we're only changing those that start as 1, right? We only change the ones that start as 1. Actually, we're coloring with 2. Sorry, color is going to be 2, so this is what we're going to change it to. But our starting color is going to be 1. The one where it, like we were given SC and SR equal to 1. So this element right here, and we're gonna record what color is that element at the beginning. So we record it as 1, and then I'm gonna change that element to 2. And what I'm gonna do to check all of its adjacents is I'm gonna create a queue. So a queue is a data structure that is like as you would imagine if you're trying to go in a queue in a bank. If you get there first, you're served first. It's first come, first serve. And so you start putting imagine it's a list of numbers. You start putting numbers on that list, in like let's say from left to right. And when you're trying to take out a number from that list, you take it from the beginning, because that's the one that would have got there first. You take it from the beginning, and you take it from the beginning, and you take it from the beginning. But when you're appending, you append them at the end. In contrast with a stack, which we did for valid parentheses solution last stream. In a stack, what you do is you put elements to the right, and you take them out from the right. You take out the last element that you put at the top, because remember, we have a stack of plates. We put a plate at the top, and when we're trying to take an element, a plate, we take it from the top. So we take the last one we put in. But in this case, we're using a queue. So we take out the first one we put in. We put it first come, first serve, basically. So we're gonna use a queue, and in this queue, what we're gonna insert are gonna be the indexes that we need to check. So what are the indexes that we need to check? All of the adjacent ones that actually not that we need to check, the indexes that we need to change. What are the indexes that we need to change? Those that are adjacent to the current index we're checking, that also start with the starting color of 1. So we check all of the adjacent ones. Is this color 1? No. Is this color 1? No. Is this color 1? Yes. We put it in our queue. So we're gonna put here, it's gonna be 0, 1, 2, 0, 1, 2. So this is going to be element 0, 1. We're going to put it in our queue. And then here, we check this one. Is it 1? Yes. Let's put it in the queue. So we put element 0. This is going to be 1, 0. We put those in our queue. Right? And we've changed this color. And we've done this part, and we've already added all of its neighbors to it. So we can go to the next one that we need to change. So we go here. And then we change it. Like we did with the previous one. So we go to 0, 1 and we change it to 2. And then we check its neighbors. So this neighbor should become 2. This neighbor should become 2. This neighbor's already 2, so we don't need to change it again. And there's no more neighbors. So we're gonna add these 2 to our queue and remove the current one. So we've removed the current one because we've already visited it. And we're gonna add 2 more. Like you saw, we do them in like order from left to right, but we added at the end. So we're gonna add here to the end. We're gonna add index 0, 2 and index 0, 0. And then we're gonna repeat the process. So we would go next to 1, 0. We go here. We go here, and then we check its neighbors. This is 1. This is 1, and we add those to the queue. But 0, 0 is already in the queue, so we don't need to add that again. So we're also gonna use for this problem. We're gonna use a set where we're gonna store the positions that we've already visited or that we've already added to the queue, so we don't add them again, right? Because we don't want to like convert this to 2 and then we have to go in there again and then we find out that we have already converted it to 2. We've already painted it as 2, so we don't want to do that. So what we're gonna do instead is we have a set, and we store in that set the ones that we've already added, so we don't add them again. So in this case, we would add 2, 0, but we wouldn't add 0, 0 because it's already in the queue. And then we would visit 0, 2, 0, 0, add their neighbors until we don't have any more elements left in this queue, because we visited all of the elements that we needed to visit. We visited all of the possible neighbors. Right? You could do this recursively in a different way, but I decided to go for it iteratively. So let's program that solution. So we have SR, SC, and color. So we're gonna, like I said, initialize the starting color as image SC SR. And let me just double check the constraints. So SR is gonna be less than M. M is the rows. SC. Okay. So M is the rows, and so it should be. See, these don't help, but I think since okay, M is the total amount of rows. Oh, it gives you rows and columns. So okay, never mind. That's why that's what the R and C mean. So SR is the starting row and SC is the starting column. Okay. So our starting color is going to be whatever's in the starting row and the starting column. And then we're going to create a queue. So queue. Actually, why am I programming here? Okay, let's copy this over to my Neovim. And this is going to be what's the topic? Arrays? Yeah. Okay. And then so we're doing like array problems today. This is 733. Okay, so we're gonna create a queue of pairs of integers, because we're gonna store positions that we need to check. That's an X and a Y, or a row and a column position that we need to check. So we're gonna store pairs in there, and that's gonna be our queue. And then to start, we're gonna add our starting row and column to that queue, because that's the first one that we need to ever check. So q dot push, I think it's push. So check. Q C++. Push, yeah. Q dot push. We're gonna push SRSC. Then, while actually let me just do that because my NeoVim wants to do it. While our Q isn't empty, so while not Q dot empty, what are we gonna do? First, we're gonna color the current index. So first, let's get out the element. So int cur is gonna be equal to q dot front, and then we're gonna do q dot pop. So we're gonna get the first element, and then image of cur dot first, cur dot second is going to be equal to our color. We're going to color it the right color. Another thing that we need to add here is our set to check the ones we visited already. So let's create that set. Set of pair int, and you're going to call it st for set. And to start, we're going to do set.insert srsc. Okay? So we colored the index that we're currently visiting, and then we check its neighbors. So to check its neighbors, we're gonna say, I'm just gonna do it manually. It's gonna be a little bit tedious, but bear with me. So if and actually let me do cur row and cur column. Cur row is going to be equal to cur dot first. Cur column is going to be to cur dot second. And then here we can replace these with cur row and cur column. So if cur r is so we're going to check first. Let's check the left one. So if cur column minus 1 is bigger than 0, right? So we check if there's, because if we're in an edge, there's not going to be a left neighbor. But if that is bigger than 0, then also image of cur r and then cur column minus 1 is going to be equal to our starting color. If it's the same color as the starting one, then we're going to color it. So we're going to do the same process that we did at the beginning. We're going to do q dot push, but in this case it's going to be cur row and then cur column minus 1. We're also going to insert it in our set.insert cur r and then cur column minus 1. And then after we've done this, we've added it to the queue that we need to do, and that's it. Actually, in this if right here, we also need to check if we haven't added it yet. So if that is possible, and also let me see set C++ just to see the methods. Okay, I'm just gonna use count. So we're gonna say set.count cur r cur c minus 1 is equal to 0. That's right. So we're gonna check that we haven't added it to our current set as well. Then we add it to our queue. If we've already added that to our queue before, we don't add it again. If it's not the starting color, we don't add it again. If it's not a valid position, so that means it falls outside of the grid that we were given, we don't check it. Okay, so we've checked the left. Now let's check the top. Let's check the top. So if cur row minus 1 is bigger than 0, and we're gonna change it here. So cur row minus 1, but we still stay in the same column. So if that's not in our set, and then we also update it here, then we push it, and we have to update these here. Perfect. Okay, we've done the top. Now we need to do the right one. The right one is gonna be cur C. If cur C plus 1, and now we're gonna change the sign, so it's gonna be less than or equal, or actually less than, and these should be actually bigger than or equal, not bigger than, because 0 is a valid number in there. So if cur C is less than image.length, image.size, and actually this is going to be image0.size, because it's a square grid, or a rectangular one, I guess, and we're checking columns. Okay, perfect. Image0.size, and this is going to be cur column plus 1, and this is going to be cur column plus 1, and this is going to be cur column plus 1, cur column plus 1. This is why I don't like doing this manually. It's very tedious, and you can make a lot of mistakes doing it, but it's kind of necessary. I think there's a better way. I can think Python that I could replicate here, but honestly, it's more boiler. It's about the same to write it in C++. In Python, it's like way easier to do that way, but here it's probably the same. And then we're gonna do the same with rows, but in this case, we're gonna check that it's less than image.size. And stack.count, so it's gonna be plus 1, plus 1, plus 1, plus 1. Okay, and we repeat that process, and at the end, I don't think we return anything in this. Oh, it's expecting. How does it want it to return it? Return the modified image after performing the flood fill. So it gives us the image itself. I mean, technically you could just get the answer from this, but it wants us to return it. So it's actually at the end just return image. Let me double check the answer. So we have our starting column, our starting color that we check. We have a queue as set. We add the starting position to queue and set. Well, our queue is not empty. We color it the right color. We check its neighbors. So we check column minus 1, column minus 1, column minus 1, column minus 1. Yep. We check row minus 1, bigger than or equal to 0. Row minus 1, row minus 1, row minus 1, row minus 1. Yep. We check column plus 1, less than the size of the columns. Column plus 1, column plus 1, column plus 1, column plus 1, and then we check the rows. That has to be less than the size of the rows. Plus 1, plus 1, plus 1, plus 1, and then at the end we return the image. Yeah. Actually, zoom in a little bit here, because sometimes I feel like for my answers, like they're too small, and like also like the problem set. So let's try my solution. No variable conversion from, oh, right, because this is not an int. This is actually a pair. I wish you could unpack variables like you can do in other languages, so I don't have to like first put it into a pair and then separate it into two, but whatever, man. Passes. Let's go. This beats 5.86. Probably if I run it again, I could reach here. It doesn't matter. Okay, that is flood fill. Let's go for lowest common ancestor of a binary search tree. Let me think, because I put it on the max, so this is like actually like excessive, because this is like a training plan for interviews. where you're supposed to do each week, you're supposed to do like this amount, and I put it at the max amount that you can do. Can I actually like finish like 13 problems in one stream? Probably not. I think this is better like at least at the beginning, because they're easy, so I can do them pretty quickly, to do half of a week and then do half of the week on the other one. Keep going. Okay. Oh, this is easy, but it's actually a medium problem here on LeetCode. Maybe it's easier. I mean, it has a 70.5 acceptance rate, so maybe it's easier than it looks, or than it says here. Okay. 235. Lowest common ancestor of a binary search tree. Given a binary search tree, find the lowest common ancestor node of two given nodes in the BST. According to the definition of LCA in Wikipedia, the lowest common ancestor is defined between two nodes P and Q as the lowest node in T, in the tree, that has both P and Q as descendants, where we allow a node to be a descendant of itself. Interesting. So we have this tree. We're given P and Q as 2 and 8. What's the lowest common ancestor? 6. So basically, what's the lowest parent, or the lowest node that is the parent of P and Q? Considering that P is a parent of P and Q is a parent of Q, which is just something added to the definition, I guess. Okay, so we have this example where we have 2 and 8. We have this example where we have 2 and 4, and the lowest common ancestor is 4. And we have this example where we have 2, 1, and we given those two numbers, and then the highest one. How do we approach this? I think let's just draw it. So let me draw this example right here. We have 6, 2, 8. Is there always a lowest common ancestor? Yes. Yes, there has to be. Because the minute, like, the root of the tree is always gonna be an ancestor of two nodes. Any two nodes in the tree have to be descendants of the root of the tree. Right? We're just trying to find the one that's the lowest. The one that goes, like, further down. Let's keep drawing the tree. So 6, 2, 8, 0, 4, 3, 5, 7, and 9. And then R, P, and Q are 2 and 8. So P, Q. Now you could say for this example, like, oh, you start from P and Q, you go up until P and Q, like, you keep going up the tree until P and Q are the same. But no, you can't do that, because you can't do that because in this case, for example, we have 2 and 4. If you keep going up, they're never gonna match. I mean, they're gonna match at 6, but no, like at 6 is not gonna be lowest common ancestors. Like if you have 2 and 4 right here, and you go up, like this one goes up here, this one goes up here, and they're never gonna be the same until they reach the top, where actually the lowest common ancestor would be this. One way we're told that this is a BST. Does that come into play somehow? Because I can think of a way you can do it, and it's, oh, actually, yeah, BST helps us find the element, and I think I have the answer. Let's try it out. So my way is, let's say this is P. Yeah, okay. Let's say this is P and this is Q. We have 0 and 4. So we're gonna look for one of the elements, and we're gonna record the route that we use to reach that element. So in a BST, okay, so maybe I should explain this. A BST is a binary search tree, and like we did binary search before, where you like look for an element by checking the element and then checking if it's to the left or to the right. This is basically a representation of that. So if you're trying to look up the element 4, you can use this tree to find the element 4 in your list. So you start at the top, you see 6. Is 6 bigger than or less than 4? It's bigger than 4, so we check the left. All of the elements to the left of 6, or in the left subtree, are going to be less than 6. If you see here, 0, 2, 3, 4, 5, they're all less than 6. And all of the elements in the right subtree are bigger than 6. That's the constraint for a binary search tree. And it just makes it easier for you to find an element in that tree. And that is true for all of the subtrees. So this subtree is true, this subtree is true, even single nodes is true. It's always true. So you can use that to search. So for example, if we're finding 7, actually we're doing 4. If we're looking for 4, you see 4 is less than 6, so we go to a left subtree. 4 is bigger than 2, we go to a right subtree. Okay, we found 4. If we're looking for 7, 7 is bigger than 6, but it's less than 8, so boop, we found 7. That's how a binary search tree works. The method I'm proposing to find the lowest common ancestor is going to be start at the top and look for one of the elements and record its route. So let's look for our Q, which is 0. So our route's going to start at the top with 6. Then it's going to go 2. Then it's going to go 0. We're going to go 6. Okay, is 0 less than 6? Yes. Is 0 less than 2? Yes. Okay, we've reached it. So it's going to go 6 to 0. Now we do the same process for P. Okay, we go 6. Is 4 less than 6? Yes. We go to the left. We go to 2. Is 4 bigger than 2? Yes. We go to the right. We go to 4. We found it. These are the two routes. Which one is the lowest common ancestor? The last part where both routes are matching. That is the insight that I'm using here. So when we record the first route and we're going the second route, we go, does this match the first element on our first route? Yes. Does this match the second element on our second route? Yes. Once it stops matching, we know that the previous element we checked, that's the lowest common ancestor. Let's do an example for another set of 2. Let's do, for example, 5 and 0. So we record here. Let's go the path to 5. So the path to 5 is going to be 6. Then we're going to go in the left subtree because 5 is less than 6. We're going to go to 2. Then we're going to go in the right subtree because 5 is bigger than 2. We go to 4. Then we go in the right subtree again. And we get to 5 because 5 is bigger than 4 and we get to 5. Then we do the same process for Q. We go 6, 2, 0. 0 doesn't match, it's not 4. So our lowest common ancestor is the one before, it's 2. And that's what we're going to return. That's what we're going to return. There is a case here where a lowest common ancestor is an ancestor of itself. Does it still match? Can P and Q be the same? Like that's an edge case that we need to worry about. P is not equal to Q. Okay. But let's do an example where the lowest common ancestor is one of P or Q. So in the example where P is here and Q is here. So we go for 4, we're going to go 6, 2, 4. For 2, we're going to go 6, 2. Yeah, so this algorithm would still work because we record the last one that matches the previous one. The last one that matches the other path. And then we record it, and then once it changes, then we stop. We don't need to check anymore. So yeah, this would work. Okay, let's program it. This is it's gonna be trees. What's the topic? What do we think the topic is? Tree. Binary search tree. I'm just gonna create a directory for trees. Do I have one? Yeah. And then tree 235.cpp. Just copy this whole thing. Okay, how are we gonna record the path? I'm just gonna create an array. Yeah, let's just do an array. Actually, this is gonna be a vector. Vector of int path 1. Okay? And then let's find what path 1 is. So I'm gonna create a search function here. I'm gonna create a search function. Yeah, I'm gonna create okay. So we're gonna return nothing. We're gonna create it's gonna be called get path to node, and it's gonna receive a root. It's gonna receive the node. We're gonna call it X. And then it's also gonna receive, actually no, we're gonna just return a vector, which is gonna be the path. Okay. So now let's create that path. So we create that vector int path, and then what if the element doesn't exist? It's always it's guaranteed to exist. P and Q will exist in the VST. Okay, we don't need to worry about them not existing. Okay, so we're gonna create a current node. Free node cur is gonna be equal to root, and then while cur does not equal to x, so while we haven't reached our final destination, like our final node that we're looking for, if our cur.val, and this should actually be not dot but that, if our cur val is less than our x val, what do? If our current val is less than it, we check the right. We check the right. So cur is gonna be equal to cur right. Otherwise, cur is gonna be equal to cur left. And then we're gonna record the path here. So path.pushback cur.val. Okay. And we haven't covered the condition here where like it's not the same, but we have, because here we check that it's not the same before we check the next. So we only need to check if it's less, and if not, it's bigger. And we check the other subtree. And at the end, we return path. Okay, so path to P is gonna be equal to get path to node of the root and P. And then to find the lowest common ancestor, so LCA, we're gonna start it at root. Oh, we return a tree node. Okay. So maybe actually here we return a vector of tree node. And then vector of tree node. We push back just per. Yep. Okay, so path to P. We received the path to P is just a list of nodes. Now let's go through that list. We could have done this different. It's fine. It's fine. Yeah, I don't actually need to do 2 searches. I can just do 1. Okay, I'll do this approach first, and then I'll do the other one, just to like complement it. Okay, so we have the path to P. Now we check if that matches the path to Q, or up until when it matches it. So we have tree node LCA is going to be equal to root. And then, yeah, LCA is going to be equal to root, while LCA, and then we're going to create int current index is going to be equal to 0. Yeah, this is not the best way to do this, but it should work. While LCA does not equal, or while LCA equals path to P of current index, so while the path matches, basically, we're gonna find the next node. I'm just gonna copy this logic a little bit. So we're gonna increment our current index first of all. We don't need to add anything to the path anymore. And then all of these that say cur should be changed to LCA. There's one other thing here. There's one other thing here. And it is we need to store the one, the latest one that worked. So maybe let's create, this is kind of repetitive, but let's create a cur. I think you might have to do this. Equal to also the root, and instead of doing LCA, we do per. But then we update LCA with the one that worked. And then at the end we return LCA. Yeah, so we're just keeping in LCA the last one that ever like actually worked. That was the last one that matched the 2 paths. Let's see. Path to P, no viable conversion. Right. I need to update this here. Use of undeclared identifier X. Okay, well, let's find where X is. We're trying to look not X but Q. Q the val. Runtime error, heap buffer overflow on address. So heap buffer overflow, where does this reach it? Line 17, chart 16. What's our line 17? Oh. Okay. So while per index is less than path to P dot size and this, because if we run out of list, then we're gonna get an overflow. This one is incorrect. Output 6, expected 2. Oh, okay, in the path to P we have to include P. So path dot push back cur. We have to include P in there. Let's see. 2, 1, 1, 2. The output should be 1, but it's expected 2. Oh, we have to pick the highest one. Okay, maybe that's why this approach doesn't work. So we're just gonna try my second approach. So I realized that we're doing a little bit of repetitive work. And instead, what we should do should be this. So let's say this is P and this is Q. We should just start at the top, right? And then search for both at the same time. Instead of like searching for one first and then searching the other, we just search for both at the same time. The moment we don't like our search process like differs for both of them, that's our lowest common ancestor. So let me run through that. So we're looking for 5 and 0. We start at 6. Are 5 and 0 both less than 6? Yes. So we need to go to a left subtree for both of them. So we go down. Here, are 0 and 5 both less than 2 or both higher than 2? No, because 0 is less than 2, but 5 is higher than 2. So in that case, in that case, this is our lowest common ancestor, because in this point is where you would actually like fork the route in which you would reach those nodes. An edge case there is if we reach one of the nodes, that's our lowest common ancestor. So if our P and Q, instead of being 0 and 5, they are 2 and 4. Once we reach 2, we're done. Because 2 is like, this is the highest one of the two of them. And we know that 4 is going to be a child of it. Otherwise, we would have forked the path before. And we don't need to keep checking anymore. So 2, like there's an edge case there. But 2 cases we need to check for. Like if they're in the same path, and if we've reached one of the 2. Okay, so let's change our approach a little bit. We don't need this get path to node anymore. We don't need this anymore. I mean, we can. Let's have it just in case. We don't need this cur index. We don't need a path to P. See how it becomes so much easier? We don't need to do 2 passes. Before we were doing 2 passes of the answer. And then let me just copy this whole thing, and then we can do it in the open. So G, paste, and then DGG. Okay, so we start at our root. And then here we're gonna do just a well true. You're just gonna keep looping until I say we need to stop. We don't need this anymore. We don't need this anymore. Okay, so we need to check that they're both less than, or they're both bigger than, or we've reached my current node. So let's do the last, like the edge case first. If LCA is equal to P, or LCA is equal to Q, we return LCA. And then let me update this here, so it's going to be LCA, 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 LCA. If my LCA Um, if my okay, if p val is less than LCA val and q val is less than LCA val, then we go into a left subtree. Actually, so it should be changed to left. Else, if this, so we're going to change the signs here. So if p val is bigger than LCA val and q val is bigger than LCA val, then LCA is going to be LCA right. We'll just do the other case where we go into a right subtree. Otherwise, so we already checked. Have we reached either one of the nodes? No. Are the nodes both in the left subtree? No. Are the nodes both in the right subtree? No. Then what must be the problem? It must be that one node is to the left subtree and one node is to the right subtree. In which case, we've reached our common ancestor. We can return. And then here we're just gonna return null PTR, because we would never reach here in a walkthrough. We're always gonna reach an LCA, but just in case, I mean, we should never reach this. We should never break out of it. So I'm just gonna send this. Does this work? Yes. Let me see something. Why when I paste it, it looks like this? Huh. Weird. So it works for test cases. Let's submit it. Okay, I was just overcomplicating it. But very simple. We just search for both nodes at the same time. The point the paths differ in our search, we've reached our lowest common ancestor, because they're not going to be in the same subtree anymore. Okay, done. See, that was kind of like a medium. I mean, I realize the algorithm is like pretty simple, but the actual implementation, like, there's some things you need to think about. So I agree it's a medium. It took me a little bit more effort than the previous ones. Ooh, balanced binary tree. Given a binary tree, determine if it is height balanced. A height balanced binary tree is a binary tree in which the depth of the two subtrees and of every node never differs by more than 1. This reminds me of my data structures and algorithms class, but let's go through the examples. So we have this tree, and the output is true. The depth of two subtrees of every node never differs by more than 1. So what is the depth of a subtree, or the height? The height is the amount of nodes in the path that takes us, like the amount of the biggest amount of nodes that takes us to the bottom. I don't know if that makes sense. Okay, so for example here, the height of 1 is gonna be the longest path to the bottom. So 1, 2, 3. That's the height, 3. We like the height of the right subtree of this 2 is just 0. It's height 0 because it doesn't have any children. It's already at the bottom. We always take the max height between the left and the right subtree, and that's gonna be the height of the current subtree. And the height is, like I mentioned, do the path to the bottom and then the largest one. So what do we need to solve this problem? We need two things. We need something to calculate the height of a tree, and then we need to compare the height of the two subtrees, the left one and the right one, and then check that they don't differ by more than 1. So let's check the examples. What's the height of this one? 0. What's the height of this one? 1, because the max path to the bottom is just 1. To the left or to the right, it doesn't matter. What's the height of this subtree? 1, 2. What's the height of like 1, 2. What's the height of this subtree? 0. It differs by more than 1, so it is unbalanced. Okay, pretty simple. So the important part here is the algorithm, or how to get the height of a tree, and it's gonna be a recursive algorithm. So if we have something like this, the way we're gonna calculate here is gonna be a recursive algorithm where it goes, so the height of this node, let's number them to make it easier. 4, 5, 6. The height of 1 is gonna be equal to the max of, and this is where the recursive part comes in, the max of the height of 2 and the height of 3. Right? And what's our base case? Because this is gonna keep running down the tree. What's our base case? Because otherwise we're just gonna keep recurring infinitely, or we're gonna get to an error here when it tries to calculate the height of no. Our base case is when we reach a leaf node, like this one. A leaf node is a node that doesn't have any children. The height of that is gonna be 0. So the height of a leaf, in my definition, you can define it in different ways. I remember my data structures class, they defined it like different, where this was height 1. But the height of a leaf is always going to be equal to 0. Right? And the height of... Oh, actually, it's going to be 1 plus the max of the height of them too. Right? Yeah. Because you can't just, because if it was just this equal to the max, then it would be 0, 0, 0, all of them would be 0. You have to do 1, because technically you have to reach that node, so you add 1 to resolve. So the height of any node, any internal node, is going to be 1 plus the max of the height between its two, the left subtree and the right subtree. And the height of a leaf is going to be 0. Okay, what happens if you have, if like there's no right subtree? So if we have something like this, we have 1 and 2. When it tries to check the height of the right subtree, it's going to be the height of null, and there's going to be an error there. What are we going to do for that? So we're going to say that the height of null, if we ever reach null, the height of null is going to be -1. Okay? So in the case in which we have a leaf node, I mean, we already have that case. Oh, actually, we don't need to cover that then, because when it reaches like a leaf node, it takes the max of the left and right subtree. They're both going to be null. They're both going to equal -1. The max of those two is going to be -1. You're going to add 1 to that, and the leaf is going to be 0. So we only need this base case. We don't need the other base case. So that's how we're going to calculate it. So the height of any node is going to be equal to 1 plus the max height of the left subtree and the right subtree, and the height of null is going to be equal to -1. Perfect. Okay. 235, we're done with this. And now, what problem are we solving? 110. 3/110.cpp. How's it going, Sean? How are you doing? I'm solving right now balanced binary tree, which, like, it's just pretty much my DSA class. Just a reminder of it. Okay, so as balanced, we need to define a function to find the height. So int height is gonna be, we're gonna get the height of a node. And the way we're gonna do this is if root equals null, PTR, or no, then we're gonna return -1. Otherwise, return the 1 plus the max of the height of root left and root, oh, the max of height of root left and the height of root right. Type shit, you got this? Thanks. I had to think it a little bit because I haven't done it in a while, but it's pretty simple. And then here, when in its balance, we're gonna check that they don't differ by more than they don't differ by more than 1. And we need to do that for every subtree. That's another one. So if the height of root left, and we're just gonna take the ABS, the absolute value. If the ABS of the height of root left and the height of root right, actually I need to write it out. If the difference between those two is bigger than 1, we return false. Otherwise, oh, actually, if we reach, if root equals no, we're just gonna return true. And then here, we're gonna, so if we ever reach a case where it's not true, then the whole tree is not true. But if we haven't reached a case where it's not balanced, then we're gonna return is balanced root left and is balanced root right. So both of the left and the right subtree have to be balanced for the whole tree to be balanced, and we need to check every possible subtree. Let's see. Oh, I misspelled right. Everything else should be spelled correctly, I think. No matching function call for ABS. Does ABS not exist in C++? Absolute value C++. Is this like a Python thing that I'm messing up? Yeah. Where is the ABS? Oh, I need to actually do an operation here. Height, like the difference between the two. And I actually need to add another parenthesis here. Is if the ABS of these two, if the ABS of the difference is bigger than 1. Yeah. C. No member name flood fill in solution. This is the wrong problem. Okay. Nice. Let's go. Hey, balanced binary tree, done. Linked list cycle, I like this one. Do I have a linked list? Yeah. So mvim linked list 141. That's a good beat. Done. Okay. Linked list cycle 141. Given head. Okay. 141 linked list cycle. Given head, the head of a linked list. Determine if the linked list has a cycle in it. There is a cycle in a linked list if there is some node in the list that can be reached again by continuously following the next pointer. Internally, POS is used to denote the index of the node that tail's next pointer is connected to. Note that POS is not passed as a parameter. Internally, POS is used to denote the index of the node that tail's next pointer. Oh, okay. Return true if there's a cycle in the linked list, otherwise return false. So what is POS? The node, the index of the node that tail's next pointer is connected to. I'm confused. Oh, this is not, it's just for okay. Oh, okay, so POS 0, POS minus 1. So if, like, this is just showing us where the cycle starts. But let's just use the example. So example 1, we have 3, 2, 0, minus 4, and then you see that there's a cycle here that leads us back to this number. Okay? And then the same with this one, and the same with this one. So a very straightforward solution you could do is just following the description here. There's a cycle in the linked list if there is some node in the list that can be reached again by continuously following the next pointer. So if we ever reach a position that we've already reached in the past, then that means there's a cycle. Otherwise, we should just go from left to right, and there should be no repeats of the numbers. So the most straightforward solution is keep track of which numbers or which nodes we've visited. If by traversing through the linked list we ever go back to to a node we've visited before, then that means there's a cycle in the list. However, if you see here in the follow-up, it says, can you solve it using O of 1 constant memory? The approach I just described, you're keeping track, you have a list where you keep track of the nodes you've visited in the past. So your memory complexity is going to be O of n, where n is the amount of nodes, because you're going to keep track of all of the possible nodes that you visited in the path. So at the end, you're going to have n nodes. So I'm not going to go for that solution, but just to explain the simple solution you can go for is, let's say you have something like this. This is the straightforward solution. If you have something like this, then you traverse the list, and then this is the list of nodes you visited. So you visit this one, you put it in the list of nodes you visited, and you keep going. You do this one, you do this one, and then you go back here, and then you check. Oh, I visited one before, therefore there's a cycle. If there wasn't a cycle, if this arrow here, if this arrow here didn't exist and it just ended the list, we would reach the end of the list, and that would be it. Like 2. Nope. It'd be like 3. Okay. If we reach the end of the list and this condition has not completed, then that means there's no cycle. Otherwise, we're just gonna keep looping around. Another like naive way to do it is if like you keep going, and if you take like you can take a look at the constraints, for example. Actually, ooh, this is a valid way of doing it. I think I did this at one point. A valid way of doing it with constant memory. And as you look at the constraints, and you see the number of nodes in the list is 10 to the 4, right? So you keep traversing the list, and if you traverse more than 10 to the 4 nodes, that means there's a cycle somewhere. And you don't need to keep any track of like which nodes you visited. You just like traverse it, and then if there's a cycle like this one, you're gonna get stuck in this loop where you go this one, 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 this one. You're gonna keep stuck in the loop, and once you visited more than 10 to the 4 nodes, then that means you reach a cycle, because there can't be any more than 10 to the 4 nodes according to the constraints. So that means you must have visited one node more than once by pigeonhole principle. That's another way you can do this, without using any memory, and it's just kind of cheating the constraints. I think the first time I did it the follow-up, I did it that way, and then I found about the other method, which is the proper solution for this, and it's using a slow and a fast pointer. And I'll show the slow and fast pointer solution. I don't think I know how to explain it, because I haven't done it in so long. But what you basically do is, let's keep that cycle in there. Let me just redo these because they're a little messy, but 1, 2, and then it goes back. So you start with 2 pointers, a slow and a fast pointer, and you begin at the beginning of the list. The slow pointer is going to move normally, so it's just going to move 1 at a time. The fast pointer is going to move 2 at a time. So in this example, we start here, we move on to the next one. The slow is going to move here, and then the fast is going to move here because it's going to go 2 ahead. Next iteration, the slow moves here, the slow moves there. Sorry, I'm having a brain fart. The slow moves here, and the fast, which was here, moves here. So now slow and fast are at the same point. That must mean there's a cycle. Because otherwise, if there was no cycle, fast would reach the end of the list before slow, and it wouldn't ever get back to where the slow pointer is. Like, you would never have a case where slow and fast are at the same point, because fast would reach the end of the list in half as much time as slow, and it would never like go back and get slow. It's like the what is it, the turtle and the tortoise and the hare or whatever. Like, if you have 2 at different speeds, the fast is always going to reach the end. It's never like slow is never going to reach fast, and fast is never going to reach slow, because they're like going at different speeds. If they ever reach the same point, that must mean there's a cycle. And how come they always reach the same point if there's a cycle? That's like a harder proof. But I think, let me see. There's a way to explain it, because there's also there's a different question where it asks you to return which node the cycle starts in, and then you can do some math to like figure it out. Let's try to figure it out together. So if I remember correctly, the explanation, you're always gonna have some part where there's no cycle, like your list is just gonna go as normal, and then there's gonna be a cycle of 1 or more nodes. So let's say there's a 3 here, and then it goes back to 1. So there's this part that doesn't have a cycle, and then this part that is part of the whole cycle. The cycle technically, what if the loop is in prime numbers? I don't understand. What do you mean? What if the loop is in prime number? Like, you're talking about the divisibility, but I think because we're doing 1 and 2, they always like match at some point. If there's a loop, but that's what I'm trying to figure it out here. So if we're going like this part, fast would never end in a loop. Like, they would never match. Yeah, so like that's the part I'm trying to prove here. Because they're not divisible by each other. I think I get what you mean, but I think because we're doing 1 and 2, that's why you can like reach each other. So let me just try to like run a little bit through the proof. Like, I don't remember how it goes, but I think it will go something like this. So we can ignore this part that doesn't have a loop, and let's say our whole linked list is just a loop. So if if we start both pointers here, and let's say the positions are 0, actually 1, 2, and 3. 1, 2, and 3. And slow and fast start here. the formula to get the next pointer of slow is gonna be s plus 1 mod n, right? So let's change this actually to like 0, 1, 2 instead of 1, 2, 3, so it actually works. 0, 1, 2 is s plus 1 mod n, and then this one is s plus 2 mod n. So what we're trying to prove is that at some point, if there's a cycle, s plus 1 mod n is going to be equal to f plus 2. To f plus 2 mod n. Why is that? Oh, I think I know why. So ignoring that there's like this part right here, if you have like a loop like this, then slow starts here, fast starts here, slow goes here, fast goes here. Let's actually do one with 4 nodes. So like just we're gonna do the even example and it's gonna match a little bit easier. Slow and fast start here. Slow goes here, fast goes here. Oh. Then slow goes here, fast goes here. Oh, sorry, no, fast actually goes here. So at this point, whenever like fast finishes the whole loop, that means small is half through the loop, right? Because of the speeds. Like you can finish the whole loop in half as much time as small, right? So then whenever the small completes the loop, so then small would go here and fast would go here, and then small would go here and fast matches because they're going at twice the speed. So if they both start at the same point and there's a loop, so small is gonna do the whole loop in n steps, fast is gonna do the whole loop in n over 2 steps. So fast does one whole loop, the slow one is at the half, then it does another whole loop, and they both at the beginning. Now this is in the case where they're both starting, like the loop is the whole linked list, and they're both starting in the same place. But in the case where there's a part where there's no loop, like in this one, there's gonna be a mismatch, right? Because here, like small and fast are gonna be here, then slow and fast are gonna be here, then slow is gonna go here, and fast is gonna go here. So we can now ignore this part, which is the one that doesn't have the loop. And now our problem is we have the same like cycle, but they're not starting at the same position. Slow is starting here, and fast is starting here. Now, this is the second case where it makes the problem more complicated. So we proved that if the whole linked list is a cycle, and they both start at the same position, they're gonna reach the same position again after 2 loops of the fast pointer. Because of what we proved, like it goes at half the speed. So slow is gonna do one lap, and then in the same time that fast does 2 laps. Now, if they both don't start at the same place, let's sort of do let's do the simulation. Also, there's another case where the number of nodes, so we've done it with even and it's very well split. But what if they're not even? So if it's an odd number, let's first do that. I think that might be a little bit easier to prove than the next. So let's say they both start at the beginning and there's an odd amount of nodes. Small goes here, fast goes here. Okay. And now then slow goes where fast is, and fast goes here, and then slow goes where fast is. The slow goes to the beginning, and fast gets to the beginning. So it does work. This does work. I think the reason why is because if you double the, like, because you're doing the loop 2 times, it's gonna become an even number, and that's why it's gonna end up matching. Yeah. So if you have an even number and you double it, because you're doing the loop 2 times with fast, it's gonna be an even number, so it's gonna match. If you do with an odd number, if you double that, it's gonna become an even number, and then it's gonna match. So we've done this proof. Perfect. Now we need to do a second proof, which is a little bit harder. And the second proof is, how do we know that if they start at 2 different places, if slow starts here and fast starts here, that they're gonna end up reaching the same point at some point. So slow, let's do a simulation. So slow would go here, fast would go here, then slow would go here, fast would go here, then slow would go here, and fast would match. That is the case for this. So it matches before we reach the end of the loop, and it matches it exactly one, like, remember, like, slow started here and fast started here. They were 1 away from each other. In this case, it matches it 1 before the end, before slow finishes the whole loop. I don't think that's a coincidence. I think that must come into play here. So let's do another simulation. Let's say that slow starts at the beginning, fast starts 2 away. So they should, in my, like, in what my intuition, they should both match here. So let's do the simulation. So slow goes here, fast goes here. Right? And then slow goes here, fast goes there, and they match. So yeah, they match exactly there. Now let's do one more. Let's do what if slow starts at the beginning and fast starts here. So it's 3 away from the beginning, so they should match 3 away from the end, so they should match here. Let's do a simulation. Slow goes here, fast goes here, they match. So there's something there. And a lot of this I'm kind of remembering from the proof, so it's kind of coming back. But, okay, so if I remember correctly, if you go back to this example, because of this node, when slow reaches here, they're gonna be this distance different from one another. Let's see. Let's prove that. Let's prove that with just like a simulation, because I think it's just true for all of them. Let's say there's like a -1 node here. So when they both started here, when they started the loop, slow was here and fast was here. Now they're 2 away, so they should be 2 away from each other. Slow, fast, then it goes slow, fast, and then it goes slow, fast. So they start 2 away, so this is the amount. So now we know that let's call this distance, let's call it x. So we have x, and then this is the whole distance of the loop. So in our case, the whole distance of the loop is 1, 2, 3, but let's call that y, right? And but this y, it can be split into two. It can be split, as we saw, into y is going to be equal to some number, let's say, what do we call it? N and m. N plus m. And that's going to be how, like, the distance between the two at the beginning and then the remaining of that. So m is going to be actually like y minus m. It will make sense. But we have y is going to be equal to n plus m. So n is going to be the distance they start apart from each other. And m is going to be the remaining distance. So this formula here is not x plus y. And actually, as we saw here, as we proved before, the distance that they're going to start separated from each other is going to be equal to the distance that is the distance away from the loop. We proved that before. So like here, if they start 2 away from the loop, they're going to start 2 apart from each other. If they start 3 away from the loop, they're going to start 3 apart from each other. So this is actually going to be the whole distance of the linked list is going to be x, the portion with no loop, plus x plus y minus x. And then y, we had like before, like the length of the loop. Y equals the length of the loop. Okay? So now let's simplify this. X plus x plus 1, x plus 1, y minus x, that you would just subtract the x and it's going to be x plus y. So that doesn't help. So let's keep it like this. How does that help us find that they're gonna always reach the same point? So if they start one away from each other and it's a loop, okay, so in this case, for f to reach s, how much is it away from s? So in our case, it's going to be y minus x. So f is y minus x away from s. And it goes 2 at a time. Oh, I see. So f needs to reach s, and f is y minus x steps away from s, right? So in this case, since it's a loop, we're gonna say that f is behind s and it needs to catch up to it. S is moving forward by 1. F is moving forward by 2, right? So like this distance, every step what we're doing is we're adding 1 to the distance because S is getting 1 away from F, and then we're subtracting 2 from the distance because this is getting 2 closer. And if you simplify this, plus 1 minus 2 is going to be minus 1. So we're getting 1 step closer every loop to S. So we're going to eventually reach it. Because we're behind S, it's moving 1, this one's moving 2. It's getting closer by 1 on every time we iterate. So eventually it's gonna reach it because it's going 1, 1, 1 is making that distance smaller, and it's never gonna be a mismatch. So that's the part of the mismatch. But other than like the proof that we did with the loop, it's that F is getting 1 step closer to S every iteration because of the way if there's a loop, because of the way they work. So that's our proof. That's the whole proof we need for this problem. And just so it's repeatable for shorts, I'm just gonna redo it. Sorry for it's gonna be a little bit tedious, but like the part where we need this x and x plus y minus x or whatever, it's for finding the start of the loop. But I'm gonna do the follow-up problem after this. Similar question, linked list cycle 2. This is the question where it asks you like, oh, where is the start of the loop? We're gonna use this to answer that. Let me see, new, can I open another window? Yes. Okay. Let me do that. Let me do the whole explanation. Let me do the whole explanation for the problem, for like this problem specifically. Okay, so let me go back to the example. So let's use this example for me to explain the problem and how we're gonna solve it with slow and fast pointers. So we have 3, 2, 0, and -4. And then -4 links back to 2. Slow and fast both start here. Now there's two cases. Either there's a loop in the list, or there's no loop. If there's no loop, our fast pointer is going to move ahead 2, and our slow pointer is going to move ahead 1. So let's do the first example where there's no loop. If there's no loop in the list, it's going to be like a race between the tortoise and the hare. So this is going to move forward 1, this is going to move forward 2. And what's going to happen is that the fast pointer, it's going to reach the end of the list in half as much time as the slow pointer because it's twice as fast, right? That is pretty simple. Like it's like fast is moving twice as fast as slow, so it's going to reach the end of the list if there's no cycle in half as much time as slow because it's moving twice as fast. In that case we're agreeing there, like it's pretty simple. Now, what if there is what if there's a loop? That means like if there's a loop, that means we're not going to reach the end of the list. And what I'm trying to prove here is that they're going to reach each other. So slow and fast both start here. And what's going to happen is eventually both of them are going to reach the beginning of the loop. So this part, as you can see, there's no loop in it, but this is the whole part of the loop. Eventually they're both going to be in this loop because they're going to keep moving forward, and a slow is going to eventually reach the start of the loop, and they're going to start going around it together. Now because there's a loop, we could say that now when they enter the loop, the distance between S and F, like it's gonna be this part, right? So F is basically trying to catch up to S. So since there's a loop, we're reframing the problem where like now F is looping S and it's trying to catch up to it. Now we know, let's say that S is like the distance between F and S, so like F is behind S, the distance between them two is going to be equal to X. We're just going to call it X. Now what happens every iteration of a problem or a program? S is going to move forward 1 and F is going to move forward 2. So what's going to happen to that distance X? This distance X So S is gonna get one further away from it. So we're gonna add one, because S is gonna move one to the right. So it's gonna move one further away from F. But F is gonna move two closer to it. Like it's gonna move 2 steps closer to it. So we're gonna subtract 2 from the distance between F and S. Now we can simplify this. Plus 1 minus 2 is gonna be equal to minus 1. So the distance, every loop, the distance between F and S is going to be 1 less. And if we're subtracting 1 from it, it's going to take us X amount of iterations for F and S to be in the same point in time, or like the same node. It's going to take X amount of steps for the fast pointer to reach the slow pointer again, for it to loop it. Right? This is similar to like if you had like a Formula 1 race and you have one car that was going twice as fast as the other one, the distance would get reduced. And like in this case, it's going to be reduced by 1 every time. So eventually it's going to reach it. And it's going to reach the same spot because we're only subtracting by 1. If we're subtracting by some other amount, you might miss it. And then you would have to get into like lowest common divisor or something like that. But since it's reducing by 1, eventually it's going to reach it. It's going to subtract 1 from it until it reaches the end, until they both reach the same point. So with that fact, we can now see that if there's no loop, fast is going to reach the end of the list, and then we can finish the program because we know there's an end to that list. If there is a loop, there's going to be some distance x between F and S that's going to get reduced by 1 on every iteration, and eventually fast is going to reach slow. Okay? So let's program that up. So in this case, we're asked to use 2 pointers. We're asked to find if there's a cycle in our list, and we're going to use the slow and fast pointer technique to find if such cycle exists. So we're going to create a list node slow and fast. These are 2 pointers, and they're both going to start at the head. Right? And then while fast hasn't reached the end of the list, and they're both not in the same place. So while fast next and fast next. So while it hasn't reached the end of the list, if it ever reaches the end of the list, we can return false. There's no cycle. Otherwise, if slow equals fast, if they ever reach the same point, return true. There is a cycle. Fast somehow reached slow, so return true. Otherwise, we're just gonna make slow equals slow next, and fast equals fast next. Very simple. Let's see if I didn't make a mistake. Okay, correct. Member access with a null pointer of list of type list node. Oh, there could be the case where there's an empty list. In that case, we just return false. There's no cycle. So here, so this is one of the edge cases. If the head is null, we return false. There's no cycle because there's no list. Okay, let's see. Wrong answer. They both start at head. Output true, expected false. Oh, when they first start, they are the same. So we need to check. We need to check after. Yep. Nice. Let's go. Okay. So now that we've done this, like we've done it with the follow-up, we can solve it in constant memory. Let's go into linked list cycle 2, which is like a follow-up to this question. And I think it's gonna come together with like the explanation I gave. So now, linked list cycle 2, 142. Given the head of a linked list, return the node where the cycle begins. If there's no cycle, return null. There is a cycle in a linked list. We already know the definition for this, and then POS is going to be the position where it loops back to. Okay, so we have the same examples, and we're trying to solve it with constant memory. Because we already know that we can have like a list where we store all of the nodes that we visited, and then once we visit that node again, we know that's where the loop started. Okay, so this is 141. Let's go solve 142. Perfect. Now let's go to, let me just go to this. Okay. Okay, so let's go back to the example. So how do we find out where the start of the loop is? So this is the start of the loop, right? So we're gonna have slow and fast starting at some beginning. It can be that that's the beginning of the loop. It can be that it's not. But okay, let me think. So if the start of the loop is the beginning, slow and fast are gonna meet back at this beginning, right? Because fast is gonna do 2 loops while slow does 1 because it goes at twice the speed. That seems obvious. But however, there is the case where the loop doesn't start at the beginning. It starts at some other point. So let's say here. Now, one thing we can see is that slow would let's do a simulation. So slow in the next iteration would go here, and fast would go here. So slow is at the beginning of the loop, and fast it's in the second position of the loop. So they're one apart from each other. This is the same amount as the distance between the beginning of the loop and the beginning of the linked list. It's 1. And we can prove that. Let's do another simulation, for example. Let's say this is like another node -1. They both start here. Then slow would go here, fast would go here, then fast would go here, and slow would go here. Why is that? So the distance, like this is similar to what we were saying before. So now let's consider that slow is behind fast. So the distance between slow and fast, it's going to be changing in the following way. So the distance x, fast is going to be moving forward 2, slow is going to be moving forward 1. So this distance is going to be increased by 2 because fast is moving 2 further away, and slow it's gonna be reducing it by 1 because it's moving 1 closer to fast. So this distance is gonna be increasing by 1 every time, right? And so slow is gonna be reaching the beginning of the loop. So let's call this distance between the beginning of the linked list and the beginning of the loop as x. Slow is gonna be reaching the beginning of the loop in x steps. And in those x steps, the distance between s and x is gonna be increasing by x exactly, because it's increasing by at the beginning it's 0, and it's increasing by 1 on every step. After x steps, the distance between them becomes x. So we can by that method we can prove that when s reaches the beginning of the loop, they're gonna be x steps away from each other. So this is gonna be x, and let's call the whole length of the loop, let's call it y. So then the whole length of the loop is going to be equal to, so the whole length of the linked list is going to be equal to x, the distance between this and this, plus x plus y minus x. Now, how do we find this beginning of the loop? Well, we know that the distance at the beginning of the loop between slow and fast is going to be equal to x. That's going to be the distance for like x to reach f, right? Oh, and we also know that the distance between f and s is going to be y minus x. We have it right here. That's the distance. Another insight we have is that the distance between f and s is reduced by 1 on every iteration by the proof we did earlier, because f is moving closer to it plus 2 and slow is moving further away plus 1. So 1 minus 2 is minus 1, so that distance is getting reduced by 1. We know the distance between f and s is y minus x. Right? So using all of this, how do we find the start of the loop? We know that it begins x steps away from each other. So once they reach each other, what do we know? What do we know once they reach each other? So, okay, so if I think another insight here is that if they start like this, they're gonna meet here. Yeah. So if slow starts 2 away from fast, they're gonna let's do a simulation. So slow goes here, fast goes here, slow goes here, fast goes here. So they meet there. If they begin 2 away from each other, they meet 2 away from the ending, I think. Let's add another node here. Let's add a node, let's say 5, that loops back to this 2. So if we have here slow and fast, and they start 2 away from each other, my hypothesis is that they're gonna find each other here. Actually, they're gonna find each other 2 away from the beginning, 1, 2, so like here. And let's try it out. So slow goes here, fast goes here. Then fast goes here, slow goes here. and then they meet. They actually meet here. So sorry, I actually made a mistake. They started 2 away from each other, and they met here. Why? Okay, actually, let me run a simulation. So here and here, and then here. I'm doing something wrong. Let's say it started there. Slow would move here. Fast would move. Slow goes here. Fast would go here. Then slow goes here and fast goes here. They meet in the middle. Because they're 2 away from. They were 2 away from the beginning. Now they're 2 away from the end. No, it's 1 away. Why did they meet here? Why did they meet where fast was? Let's do another, let's try out maybe another set, like another example. So they start 1 away from each other. This goes back to the beginning. Slow goes here, fast goes here. Slow goes here, fast goes here. I think I'm just getting messed up by the arrows. Let me not be lazy. So slow goes here, fast goes here. Then fast goes here, slow goes here, and then slow goes here, and fast matches. Yeah, so I think, yeah, my initial theory, I just did it wrong where I wasn't doing the sequencing right, but they started 1 away from the beginning of the loop, and they end 1 away from the beginning of the loop. Okay. Now, let's see if they start 2 away from the beginning of the loop. So now let's say fast starts here. My prediction is they start 2 away from the beginning of the loop. So they end. Oh, because this is the middle? So they should end the same there. So like slow goes there. Fast goes to the beginning. And then slow goes here, and then fast goes there. Yeah, so they started 2 away, they end 2 away. Now let's do one last example. Or actually, yeah, let's do one last example. Slow and fast both start here. No, they don't start there. They start here and here. I'm assuming they're gonna meet here. Yeah, and that is true because after 1 iteration, slow goes here and fast goes there, and they meet 1 away from it. Okay. So we can. So we have the the whole loop is X, which is this part. Then there's Y, which is this whole loop. Y. But we also know that the distance they start apart from each other is also X. So X plus X. X plus X plus Y minus X. Yeah, because we know that the distance that they begin apart from each other is the distance that they begin apart from each other is the distance that they start the loop apart from each other. Or no, the distance from the distance from the beginning of the loop from the beginning of the linked list to the beginning of the loop is the same distance that they start apart from each other once slow enters the loop. Okay. And so how do we find this beginning? So we know that S is at position 0 and F starts at position X. And so how many iterations is it going to take for F to reach S? So the distance between them at this beginning is going to be y minus x. And we know that that distance is getting reduced by 1 on every iteration. So it's going to take us y minus x steps to reach, for them to reach each other. Okay? So it's going to take us y minus x steps for them to reach each other. And so let's say they both reach each other here. Now how do we know to reach the beginning of the loop? Now, okay, now when they've reached each other, we know that the whole loop is y. The whole loop is y steps. The distance between them is 0 right now. Okay. So if they do another loop from here, they're gonna meet at the same point. Because once they match, we have the base case where they're starting at the same starting point, and then the fast does 2 loops while the slow does 1. So we don't need to do like a whole lap. But how do we find when how do we find the beginning of the loop? Okay, let me think. How do we find the beginning of the loop? We know that it's gonna take us y minus x steps for them to reach each other. And then they're gonna reach each other some amount. Like they're gonna reach each other after y minus x steps. How do we find it? Because if we find okay, another insight is the point where they will find each other is gonna be equal to x, I believe. Like what did we do before? Before we had that if once they begin the loop, they started 2 away from each other, 2 away from like F was 2 away from the beginning, that they were gonna meet 2 away from the end. If it starts 1 away from the beginning, it's gonna end 1 away from the end. Like they're gonna meet 1 away from the end. So the point where they meet, what's the point where they meet? It's going to be equal to x plus y minus x. It's going to be equal to y. No, it can't be equal to y because y is the whole loop. What's the point where they meet? So if this, okay. So if f starts at position x, f starts at position x, they meet at position y minus x. Yeah, that makes sense because they're y minus x step from each other, so s is going to take y minus x steps to get there. Now, for s, like, how many steps do we need for s to reach the end of the loop, and where is f going to be based on that? So if they start here, they're gonna be here, and it's gonna take, they were one away, it's gonna take one step for s to reach the beginning of the loop. So s distance to the beginning is gonna be equal to 1, and f is gonna be here. Do you do like another loop maybe? No, because it just takes us back to the beginning position. And eventually we're gonna reach this again, and we're gonna keep cycling. Oh, okay. So like we can keep going until they match again and count the amount of steps that takes. Because once they're here, the next step in this case is for them to reach the beginning of the loop. Is that the case on the? And then we count the amount of steps that they take to reach each other again. And that's the amount that's our x, and then we count x away from the beginning, basically. Let's try that again, but with a different, so we started like this. Let's try like this. So this one goes here, this one moves 2 and matches. Now we start counting how many times do they take for them to match again, for them to do the whole loop. One, two. Actually, it should be 3. Yeah, because we need to find x. Right. Okay. I think I got it. I can explain it easier with like y and x instead of like doing the simulation. Okay, so our final problem is we need to find this distance x, and that's the distance from the beginning to the start of the loop. We need to find that distance x. After we have the distance x, what we need to do to find the beginning of the loop is go from the beginning of the linked list, move x steps, and we know that's going to be the beginning of the loop. Now, if now like let's say, so we have from before that's slow and fast, like there was this whole loop, and we call this whole loop y. And now slow and fast are gonna start x away from each other. So the distance between slow and fast is gonna be equal to x, right? And now it's gonna take them y minus x steps to find each other again. So y minus x steps, it's gonna take them to be at the same place. And once they're at the same place, they're gonna be at position y minus x. Yeah, they're gonna be at position... Oh my god, this is hard. They're gonna be at position y minus x. Yeah, they're gonna be at position y minus x because they're gonna start here, and this is the distance y minus x. So in this case, it's 1, 2. So this is gonna be able to move 1, 2 steps before they meet, because that's the distance between one another, and they're gonna meet in y minus x steps. So it's gonna be y plus y minus x plus y minus x. No. This is a bad way to describe it. They're gonna meet at position y minus x of the whole loop. So in this case, they would meet here in the middle. And now we do like another loop and count how many times they take to meet again. It takes them 1, 2, it takes them, okay, so first they move both here. Then S moves here and F moves here. So that's 2. Then S moves here and F moves here. That's 3. And then they both meet again. It takes them 4 steps. It takes them 4 steps to meet each other. 1, 2, 3, 4. 4 steps to do the whole cycle. That doesn't help me. That doesn't help me because that's basically the total length of the loop. Okay, how long does it take fast to do a whole loop? Let's do that. So slow would go here, fast would go here, and then okay, fast goes here and slow goes here. So by the time that F does the whole loop, S is at the beginning of the loop. So we don't actually need to count like this distance. Just that makes sense. They meet, okay, so they meet at position y minus x. They meet at some position y minus x. Oh no, they meet at position x. No. So okay, so if it starts x away, so this distance is the same as this distance. We already proved that. I'm going kind of nuts. I'm gonna take a break probably after this, go get some water. So this distance is x, and this distance is y minus x. We've seen that they are gonna meet here. What is that point? That point is oh, that, yeah, that is, so this is the distance that it's gonna take to the whole thing, but they are going to meet at position y minus x from the loop. Oh, okay, I kind of have something. Wait, let me cook it up. So they meet at position y minus x. They meet at position y minus x. They meet here. Now, by intuition, I can see that by the point that f reaches this. Actually, 1 second. So if they would start here and here, and then they would meet here. So this is the correct diagram. S would go here, F would go here, and then S would go here, F would go there. Okay, let's do the whole simulation. I've said that a lot now. This must not be a very entertaining stream, huh? Okay, S and F. S is gonna move here, F is gonna move here, and this is the beginning of the loop. So they start one away from each other. Now let's find out where they meet. It's gonna be here. S is gonna go here. F is gonna go here. Then S is gonna go here. F is gonna go there. And then S is gonna go there, and F is gonna match. They meet here. Now, S is gonna go here, F is gonna go here, S is gonna go here, F is gonna get back to where it was. Okay, S and F start here. Okay, we're at position y minus x. It's gonna take y amount of steps for S to reach back that position. Y amount of steps for them to like reach back that position, and they're gonna meet again there. How do we find X? We do y minus x minus y. Wait, no. Plus minus y plus 2x, I guess. That's how we find x. What's the distance between this and this? X. And after that, they're gonna be at the beginning loop. But we don't know when the beginning loop is. S moves here, F moves here, S moves here. F moves here. And now this is like one behind, I guess. No. S is, where's S? S goes here, F goes here, then F goes here, S goes here, then S goes here, F goes here, and then they match again. It's in 4 steps. Boom, 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 boom. How do I think through this? This distance is x. This distance is y minus x. What happens once they meet? They're never gonna meet at this point. They're never gonna meet at this point because they were mismatched. It must be something where, like, take the pointer for F when S reaches back, or like a certain point, or take the pointer for S when F reaches back like a certain point. I just can't figure out why. Or what if I don't move them both at the same time? Huh? Yeah. What if I don't move them up like at the same time? What if I leave them there? How many steps does it take for... It's gonna take me Y steps for it to reach each other. S moves here. 1, 2, 3, 4. And that's the whole 1, 2. The whole length of the loop is 1, 2, 3, 4. How many nodes in the loop is 4? How many connections? 5. Does that change if they're both here? 1, 2, 3. No, it takes me like 4 connections to get back to where it was. What if I only move fast? Fast moves here, and then moves here. It took me 2. Okay, if they start here. Fast moves here, and then it moves here. It took me 2. It's gonna take me half, so we know what the amount for Y is. But that doesn't help me. Like, I know how to figure out Y. Second. Double checking something. unrelated. I might need to like take a break and come back to this. That might be better if I have it with like a fresh mind, have time to think about it. I'm gonna give it like 10 more minutes to think about it, and then I'm gonna take a break, and then I'll come back. But oh my god, we're already at like 3 hours, and I already solved like 2 problems because then I was stuck doing this. That's crazy. But I want to solve. Okay, so I'm gonna solve this and then I'm gonna end. Yeah. Okay, unfortunate. But I want to solve this first. What are things we can do? So, what about if we do the example where there's no loop? Where there's no like beginning here, so this is 0. How many steps does it take to reach this amount? We can. Okay. It should take for them to reach each other again. SF. It should take the amount of the whole loop. So yeah, we find y. Now what we can do maybe is we count the amount of steps we've taken since the beginning. Maybe that'll help somehow. So S and F. How many steps have we done since the beginning to find each other? So then S and F, that's 1. Right? Then S and F, that's 2. Then S. Yo, how's it going? I'm still stuck on linked list cycle, but I'm trying to prove it. I already know it works. I already like okay, so no, I did the the linked list cycle 1. Now I'm doing linked list cycle 2. I know more or less how it works, and I think I almost have the answer, but I'm trying to figure something out. So okay. So we count the amount of steps we've taken since the beginning, right? And okay, so in this case, how many steps is it gonna take us to match again? Start S and F here. It's gonna go 1. They move forward. That's 1. 2. And then we do 3. Let me count that. Sorry, the two. Actually, no. F should be here, I believe. Yeah, because it did 1, 2, 3 reaches back here again. Then it did 4. No, this is not right. 1, 2, 3. Oh yeah, no, that is right. Okay. So okay, 1, 2, 3, and then like 1 second. This is 1, 2, 3, 4. This is step 4 actually. Challenge, what about you solve 2 sum in assembly? What? Oh, you want me to solve 2 sum in assembly? No, I refuse. Okay, so we've taken 4 steps. Right. So 1, 2, 3, 4. 1, 2, 3. F should be here if it was. So I think I've taken one step more than. Yeah. So we're at 3 right now. And then when we take the 4th is when we reach here. So it took us 4 to find each other. Now, the whole length of this loop is 4. Let me see. 1, 2, 3, 4, and then 1, 2, 3, 4. Yeah. Now, how much does it take us to do this whole loop again? 1, 2, 3, 4. Oh. Okay. Do we get about 2 sum with only zeros and ones? What do you mean? What are you talking about? We have the distance of like x. Okay, so we've tracked the distance of like x plus y or x plus 1 minus x. We've done this distance, and now the distance that it takes. Raw dog the binary. Yeah, sure. The distance that it takes for it to like reach again. Oh, they might not reach here again? No, they will reach it there again. Let's do a simulation. So let's do it goes S and F, that's 1. S and F, that's 2. S and F, that's 1. S and F, that's 2. So it took me 2 steps, and it's 4 total. So 2, then F and S, 3. Wait, no. 1, 2. We're at 2 so far. 2, then S and F, 3. And then S and F4. So the time that it took each other to like find like the time that it took me to get from here to where they found each other is the same time that it takes me to the whole loop. Does that give me any insights? No. I thought it would. So keeping. How do we find? I just need to find x. X is the only thing that I care about. All I need is to find distance x. Brother. Okay, so SF start here. This is distance x. Then when they start the beginning of the loop is distance x. So we have this distance is 2x, I guess. Does that help me in any way? And then this distance is y minus x. What you trying to do, by the way? What does the question want you to do? Okay, basically, I don't know if you've done this. Linked list cycle 2, you have a linked list. And I've done this before, and I know more or less how it works. I'm just trying to prove it. You have a linked list, and then you're trying to figure out if there's a cycle. That's the first point. Like, that's linked list cycle 1. You're only trying to figure out if there's a cycle in there. Linked list cycles 2 tells you more than like give me if there's a cycle or not. also tell me where does the cycle begin. So in this case, the cycle begins here at 2. In this case, the cycle begins here at 1. And you have to return that node. And I could do it like keeping track of the nodes I've visited, and then once I visit the same node again, I know that's the beginning of the loop. But we're trying to do it with constant memory, so not using like any sort of like set or like array to like keep track of the nodes we've visited. And the technique for that you use is called like a slow and fast pointer. And so like I did the beginning part, and the beginning part was, I have the other drawing here. Maybe, I don't know if this helps. Maybe I'll just do another one. The beginning part was, how you solve it is that you have 2 pointers. You have a slow and a fast pointer. And then the slow pointer moves forward 1, the fast pointer moves forward 2. Right? So on the first iteration, the slow pointer moves here, the fast moves 1, 2, it moves here. And then you keep moving them until they find each other. If they find each other, that means there's a loop, right? Because if there's no loop, the fast reaches the end of the list and there's no problem there, right? The fast reaches the end of the list and they never meet. If there's a loop, the fast basically, kind of like in a Formula 1 race where like there's a car that's going faster, it kind of loops the slow pointer and reaches it again. And then you find that there's a loop, basically. So that's the beginning problem. That's easy to prove that there's a loop using these two, the slow and the fast pointer. Now I'm trying to prove, how do we find the beginning of the loop? This is getting kind of overwhelming. Let me just close that and close that. Let me just go back to this one. So these are the things that I found so far, right? And let me just close the entire. Okay, these are the things that I found so far. If the whole list is a loop, the slow and fast pointer find each other at the beginning of the loop. They find each other at the beginning. Because are all the node values unique? Yes, but we don't care about the node values, we just care about the like unique node. So the values don't actually matter because you can compare the addresses. But so we have the slow. If the slow and fast pointers start at the beginning of the list and the whole list is a loop, they find each other at the beginning of the loop, which is the beginning of the list, because the slow does a whole loop in the time that the fast does 2 loops. Right? So that's good. But there's a problem. What if the beginning of the list is not the beginning of the loop? So if you have something like this, then where the place where they find each other is not going to be the beginning of the loop. It's going to be somewhere else. So if slow and fast start here, then they're going to move here, then they're going to move slow is gonna move here, fast is gonna move back here, and then slow is gonna move here, and fast is gonna move here. They're gonna meet there, which is not the beginning of the loop. Okay, and so the insights that I found so far is the distance that between the beginning of the linked list and the beginning of the loop, let's call it x, is the same distance as the distance between the slow and the fast pointer when the slow pointer enters the loop. This is the same distance. That's one of the insights I found. And the reason why is because like this distance x, every iteration, fast is moving 1 away from x. Because slow is moving, like the distance between slow and fast, slow is moving 1 closer to it, fast is moving 2 away from it. So if the distance, every time, this is what's going to happen to it. This is the distance. It's going to be +2 - 1, and that's basically going to simplify to +1. So if every iteration, the distance between the two of them, it's set at 1, at the beginning the distance between the two of them is 0, and it takes x steps to get from the beginning of the linked list to the beginning of the loop, then by x steps, we're going to be x distance away from each other. Right? So that's one of the insights I found. So this distance x is the same as this distance x. And if we call the distance of the whole loop, like the length of the whole loop, in this case the length of the whole loop is 3, there's 3 nodes in it, 1, 2, 3. Let's call that y. F is going to be in position x, but it's going to be y minus x away from the start of the loop. Now I have all these numbers. So like I have like x is the distance between the beginning of the linked list and the beginning of the loop. And then we have that y is the length of the loop. So x plus y is the length of the whole linked list. And then we have that y is also equal to x plus y minus x. Because there's like this part and then there's this part. Now I need to somehow find x. If I have x, I can go from the beginning of the linked list to the beginning of the loop. And I can go from the beginning of the linked list, count x steps, and that's going to be the beginning of my loop. I'm just like struggling to find x. I don't know how to find it. I know there's like I've done like I mentioned I've done this problem before. And I remember it's something like once they find each other here, you keep doing it, and then once it reaches another point, the slow is going to be at the beginning of the loop or some sort, or if you count some amount of steps, you're going to be able to find x. But I don't remember exactly how, and I'm trying to figure that out. So one thing I was thinking about was slow fast starts here. Once slow enters the loop, they're gonna be here, and this distance is the same as it's 1. I'm trying to understand. So what you say is this is your strat to find in constant time and space. Not constant time. The time is gonna be some like it's not like you're gonna be able to find it immediately, but the space is gonna be all 1. So if they start here, we also another thing that I found was that the like x. Like the point where they're both gonna meet is gonna be y minus x inside the loop. So the position y minus x is they're gonna meet here because they started 1 away from the beginning of the loop. They're gonna end 1 away from the beginning of the loop. Linear time, sorry, constant space. Yes. So they're gonna meet here. That's another thing we found. They're gonna meet at position y minus x in the loop. Now, how do I find x? Like if they do a simulation here, just to show that, they start here, then slow goes here, fast goes here, then slow goes here, and fast go here, and they meet here, which is 1 away from the end. So once they both meet here, we know that there's a loop. How do we calculate the beginning of the loop? I mean, how many steps did it take them to find each other? It took them 1, 2, 3, which is equal to x plus it took them 1, 2, 3 x plus y minus x, I think. That's why it gives me y. Yeah, because x plus this distance right here is what it takes to find each other. There, y minus x. Yeah, so x plus y minus x, that's why it gives me y. Now how do I find x? Once they're both here, how do I find x? What takes me x steps? In this case, my x is 1. It takes me 1 step to go back to the beginning position in this case, but that's not always the case. You could have it that there's like more nodes, I think. you could have it that there's like maybe let's say there's like another node here, and then there's a loop. Actually, no, let's say there's another node here, and then there's a loop. So I don't actually need to do that. So then they start 2 away from the beginning. So this distance x is 2. They start here. That means by the time that s is here, f is going to be here. It's going to be 2 away from it. So this distance x is same to this distance x. How do I find 2? They're gonna meet 2 away, so they're gonna meet here, I believe. Let me see. 1 and then yeah, they're gonna meet here. How do I find x? Because we don't know anything about this before they meet each other. Once they meet each other, we know a couple things. We know that this is position y minus x, and that we're x steps away from the beginning. We are 2 steps away from the beginning. This distance is x. This distance is y minus x. We know that once they meet each other. How do we find x? If s moves here, f moves here. Now f is at the beginning of the loop. And then they would meet each other there. Like, I feel like you have to like stagger them in some way. Maybe it's time for me to just look at the solution, because I feel like I got most of it. I'm just missing like one tiny part. What do you think? Should I look at the solution? I've been at this, I think, for like the last hour. Or maybe more. Let me see, actually. Because somebody asked me when I was doing this. It was 1:43. No, sorry. Not 3:43. So I've been like an hour and a half doing this. Like this plus the previous problem. Maybe I'll look at the solution. I just kind of want to figure it out on my own, because I remember I always struggle with this. Like I remember most of it. I just don't remember how to find like the last part. So by the time they meet each other, and I feel like it's just arithmetic. Like there's some way to do this. Like it's kind of like those problems like I see on Instagram. I don't know if you get the same, where it tells you like, oh, you have an hourglass that like takes 4 minutes to reach the bottom, and you have 2 hourglasses. How do you measure 7 minutes without like with like some restraints? So like, how do you use 2 hourglasses which take 4 minutes to finish to measure 7 minutes? And so you do something like where you stop them in like when they're in the middle, and then you do something like that. And I think it's something like that for this. I just can't figure it out for the life of me. So, okay, what do we know by the time they meet each other? We know that this distance from where they are to the beginning of the loop is x. Distance from meet to begin is going to be equal to x. Distance from like the beginning and where they meet is going to be equal to y minus x. And And we know the distance for y. We know the distance for y because that's the whole amount of steps that it took us from the beginning to reach here. So we know y. How do we find x? I can try to maybe use this. Like, technically, if I subtract y from this, I get minus x. How do I subtract y from it? Oh, this is from the beginning to where they meet. But we don't know the beginning, so we can't know that distance. We don't know the beginning of the loop. If we knew the beginning of the loop, that'd be really easy. We know y. How to find x? We don't know y minus x. Do we know y minus x? The distance between the beginning and where they meet. Can we figure that out somehow? It took us y steps from here to here. Because it's x plus y minus x. It took us y steps from the beginning to here. Can we find y minus x somehow? Because y steps to get here. This is x. Oh, I think I got it. You start again from the beginning of the list. Yeah. So once you reach here, you put another pointer here. I don't know if it's a slow or a fast one. Yeah, because you know, okay, this distance is gonna be x. So, and this distance is also x. So if you take the slow pointer from the beginning here, you move it here, and once they meet here, that's the beginning of your loop. I got it. Okay. Okay. So, okay. We know the following. We know this distance is x. We know the distance between where we are when we meet and the beginning of the loop is x. We know this and we know this. So we put a pointer at the beginning and put a pointer and like start from the pointer from where they meet, advance them one by one, and then once they meet, we're at the beginning of the loop. Got it. Okay. Let me copy a little bit of the solution that I had for this one. 142. So, okay. We have the slow, we have the fast. If there's no head, we return. What do we do if there's no head in this? We could have, so that means -1. So we return -1 here. And actually this is int. Oh, we return a list node. What do we return if there's no cycle? If there's no cycle, return null. Okay. So we return null if the list is empty, because there's no cycle if the list is empty. We do the simulation, and let me actually list node detect cycle list node head. If not head, return null. We do the simulation. Once they find each other, once slow equals fast, we do the trick. So here we don't return true. Instead, we start another pointer at the beginning. List node cur equals to head, and then while cur does not equal slow, slow equals slow next, and then cur equals cur next, and then we return cur. Once they're both the same, we return cur. If this reaches the end, we return null. Let's go back to here. Do that. Let's go. I think it's right. Yeah, let's do it. Let's go. Okay, so does that make sense? I mean, I've been rambling for like an hour and a half. I understand if it doesn't make sense, but just through the insights, we just like eventually I found the answer, which is this distance x is the same as this distance x, so you can start from here, and then eventually you're gonna reach the same point. Cool. It's gonna. I feel like I'm gonna forget it again, but at least now I have this recording I can go back to, where I look at myself basically struggle for 2 hours straight, and then eventually get to the answer. But yeah, I don't know how you would do this in an actual interview. Like, unless you know the answer already. Like, figuring this out is pretty hard unless you're not a genius. So yeah, that's like linkless cycle. Linkless cycle. I'm gonna leave this for next time. I'm gonna jump. I've been sitting down here like hitting my head against the wall for like an hour and a half. I think I need to rest. But thank you everybody for joining today. I appreciate the chatting, and actually I think Sean, I don't know if you're still here, but it helped me a lot that you were here and asking me questions, because then I was able to like recheck my assumptions, run through the whole explanation again, so thank you. But yeah, that was it for me. Thank you all for joining, and I'll see you on the next one.